Hi students, welcome to the next lecture series of Basic Electrical Engineering. Today we are going to see what are the different types of DC generators are there. So that is what we are going to study here. So in the types of DC generator, so first we will take based on excitation. So based on excitation we have two types of DC generators are there. So based on excitations, one is separately excited, another is the self excited DC generators. So in the case of the self excited DC generator, we are having shunt generator, next we have series generator, another thing is we have compound generators. So these are the different types of generators will comes under the self excited DC generators and separately excited DC generators. Let us understand what is the meaning of this separately excited and self excited DC generators. So before going to that, you require some fundamentals. So you require some fundamentals. If you draw a characteristics between, so let us draw characteristics between phi and the field current. So if you draw a field current phi and the flux phi, so the curve will be like this. So first it is going to start, it will be increased. Let us draw like this. So the curve, so if you take the curve here, so it will increases like this. So linearly it will increases, okay, reaches some. So first it will increases. So this point is a linear nature. Next after reaching that, so it will reaches to a which point? It is a saturated point. So after saturation, even though if you increase the field current, the flux cannot increase. So whenever you are decreasing the, once again, so whenever you are decreasing the flux, that is the field current, if you are decreasing, what will happen? The curve will not follow the same path, the curve will be decreases in this fashion. So here it is not following the previous path. Whenever it is increasing, it will increases like this. Whenever it is decreasing, it will be decreases. So that means even though if your the field current is 0, so it is going to maintain some flux. That flux is known as phi r. So this flux is known as residual flux. So this property is called as the retentivity property of the magnetic materials. So this curve you can see, if you observe the BH curve. So if you draw a BH curve, so in the BH curve that will be increases like this, the curve will be increases, so like this, and it is coming back and it is going like this. So this is what we have seen. So whenever it is going increasing, it will increases like this and it is coming back like this. So whenever it is coming back and it is going increases like this. So this is the BH curve. So there must be a residual flux, then only you can generate the EMF in the case of the DC generator. So if you consider a pole, it is having a field winding. So there is a possibility here. So field current is flowing like this. So there is some flux, phi is equals to mmf by, so we have flux is equals to phi is equals to mmf by reluctance. And the residual flux, here residual flux is also there. If the residual flux, so we have to connect the field winding in such a way that the residual flux must be add the main flux, that is both are adding, okay. So or the residual flux is in this direction, maybe the main flux will be opposite direction, that is a subtraction. So that we will see. So with this basics we can move on to the different types of DC generators. So when you see the different types of DC generators, first it will comes, what are the types is separately excited DC generator. First we will see separately excited DC generator. So what is the meaning of separately excited DC generator? In the name itself only you can see it is separately excited DC generator. Separately excited DC generator means, so if you draw the exactly the equivalent circuit, the field winding is getting separately excited. Here I am drawing here separately excited by a DC source. This is the field winding. So field winding RF and it is IF. So and the armature circuit will be like this. This is a separate. So armature circuit will be like this. So here the armature is connected and it is having the load is connected here. So this is the armature and the load current, this is the armature current, and here the field current will be there, and this is the load, and across the load we have the terminal voltage is V. So why it is calling as a separately excited means the generator, the field winding, okay, the field winding is separately excited, so that type of wind generator we can call it as separately excited DC generator. So if you write this electrical equivalent equations for this separately excited DC generator, so first we will have EMF generated is easy, so that is the EMF generated is easy. So we can write it as Eg is equals to V plus IA RA plus it has to supply for the brush drop. So you have the brushes here, so that has to supply the brush drop. In the problems they will give the brush drop also. BD means you understand that, so that is the brush drop. So there is some brush drop is also there in the case of DC generator. So this is the EMF generated. When you want the terminal voltage equation, if you want to write the terminal voltages, we can write as Eg minus IA RA minus brush drop. Okay, this is the terminal voltage equation. If you multiply the entire equation, this equation, if you multiply with so that is IA, so we can write as V into IA on the left hand side and Eg into IA minus IA square RA minus IA into brush drop. So this is the equation. So what is this V into IA? We can write it as, so net electrical output here, and this is the gross mechanical power developed, that is power output or power developed, whatever it may be. Next is, this is called as the copper losses, and this is the brush losses. So these are the different terms which we are going to use in the case of the separately excited DC generators. Next we will see what is the meaning of self-excited DC generator. Before going to that, so let us understand how they are going to self-excited. So why it is called as the self-excited DC generator, how they are self-excited without any external supply. Let us understand that. So for that, so in this self-excited we are already discussed, we have series generator, we have shunt generator, and we have the compound generator. Three types of generators are there in the case of this self-excited DC generator. Let us understand so how they are self-excited. So if you draw a characteristics between the EMF generated and the field curve, so EMF generated, let us draw the characteristics Eg versus Ia. This characteristics is known as open circuit characteristics. So if you draw a characteristics, so how it is getting, so it is not starting from 0, that is we are already discussed, it is starting from some point, so then it will reach us to linearly increases, then it will reach us to some a saturated point. So if it is reaches to a saturated point, so which is called as this is called as the residual flux. So let us consider a DC shunt generator. I am drawing, consider a shunt generator. Why it is called as a shunt generator, we will see. So if you observe here, so armature is connected in parallel with respect to the field winding. So that's why it is called as the, what is it is? It is called as the DC shunt generator. So this is the EMF generated. Let us consider the current. So Eg, that is armature current. After coming to this point, the armature current is divided as, that is the field current IF, and it is divided as the load current IL. This is the load here, this is the load, and the terminal voltage is V here. So here RSH is the field winding resistance. So this is the shunt generator. So in this shunt generator, if you want to get, so what is the meaning of the IF? So IF is equals to, we can write as V divided by RSH, because these are all connected in parallel. So the voltage across this RSH is also the terminal voltage V. So that is what we are going to get. IF is equals to V by RSH. So then if you want to get RSH or RF value, V by IF we can take, V by IF. So it is the slope of the curve. Slope of the curve is, the slope of this curve, just I am drawing, the graph will be like this. So which is the, so this is the field resistance graph. So if you observe here, if you observe how it is getting self excited. So for this field current, so this much of EMF is generated already. So whenever you increase the field current, so what will happen? So like this. So still it is increased, then whenever increased like this, so EMF will be still it is increased. So whenever you increased like this, so what will happen? So some extra EMF, here you can observe some extra EMF will be generated. So whenever you are going to increase the field curve, so this extra EMF, just I am highlighting here, you can observe here, this extra EMF will be generated step by step. So whenever you take a slope of this like this, so because of this what will happen? Once again the EMF is increased. That means this much of EMF is increased. So EMF generated is increased, and step by step. So because of this field current what will happen? Some more EMF will be generated. So the some more extra will be generated like this. So we are connecting the field windings, that is phi r, that is a residual flux, and will be adding this main flux. So these are to be adding with respect to the main flux. The residual flux is adding with respect to main flux. Let us consider in some other case, what will happen? If the field, that is if the field resistance is more than this, what will happen? If you observe this and one more resistance, that is RSH1 is greater than RSH, let us consider the condition here. So what will happen? The flux will be this much only, will not produce. So because it is not touching the others, okay, so it is not touching this curve. So that's why, so it should be, whenever you are increasing the field resistance is more than this value, so what will happen? The EMF will not be increases, so that the flux cannot be produced. Whether what is the maximum value you can consider for this is, you have to take a tangent for this curve. You have to take a tangent this curve. So this is called as the RC. So what is RC here? RC is the critical field resistance. RC is the critical field resistance. So beyond this, if you increase the field resistance, what will happen? You are not going to get any EMF, will not produce. So that's why the critical field resistance is very important. So what you have to do? So you should remember for the self-excited DC generators or points are, so residual flux should be there. First it will have residual flux must present, okay, residual flux must be present. Second point is, what you have to do? Flux produced should be aid the residual flux, so they both should be aided. Third one is, so it should be, the field resistance should be less than the critical field resistance, then only the EMF will be produced. So with this basics we can move to the type of the generators, okay. So this is how they are getting self excited. So let us move on to the, now let us see the shunt generator. So how we are calling it as, this is the shunt generator. If you observe in the case of the shunt generator, the field winding is connected with respect to the armature in parallel or in shunt. So that's why it is called as the shunt generator. So whenever you are connecting the field winding with respect to the armature in parallel, that is called as the shunt generator. This is the field resistance, and you have the field current and this armature current here. So here the load current IL. So load current is load, and you have the terminal voltage is V here. Let us understand clearly. So the equation. So first we will write what is the meaning of shunt generator. If a field winding connected in parallel with armature. So that type of generator we can call it as the shunt generator. Let us see the equations one by one. So if you observe here, first EMF will be generated. So at this point, if you consider this point A, at this point if you apply the KCL at node A. So let us apply KCL at node A. KCL at node A. So if you apply KCL at node A, IA is equals to, we can write it as IL plus IF. Let us understand the terminology what we are using. IL is the load current here. So IL is the load current. Next, IA is the armature current. IA is the armature current. Next, IF is the field current. IF is the field current. So these are the terminology we are using here. And EG is the EMF generated. EMF generated. And V is the terminal voltage. V is the terminal voltage. V is the terminal voltage. So let us understand. So one by one equation, if you apply the KCL at this node A, you are going to get armature current IA is equals to IL plus IF value. So as you know, the terminal voltage is present across this field winding also, because these are all connected in parallel. So we can write it as IF, we can write it as V by RF. V by RF. Next we can write EMF generated will be EG is equals to V plus IA RA plus brush drop. EG is equals to V plus IA RA plus brush drop. If you want to take the terminal voltage, we can write as EG minus IA RA minus brush drop we can write. Okay. So let us multiply this equation with respect to IA. If you multiply this equation with respect to IA, what we can write? So we will get it as EG into IA is equals to V into IA plus IA square RA plus IA into brush drop. So each terminology we will write. EG into IA is the electrical input to armature. So okay, electrical input to armature. Next is what you are going to get. So load power supplied, this is the load power supplied to the load. Okay. Next is what is IA square RA, that is copper losses. Next is this is the brush losses. So we have seen all these things. Okay. This is the terminology, and what are the equations you have to remember. Very important equations are these equations. So what is IA is, what is IA, IF, and these are all the equations you have to remember. This is very important for solving of problems. Okay. At last of this video, we will see what are the formulas are present in the entire DC generators, and this is also sometimes they are going to ask what is the EG into IA, V into IA also. Okay. Right. Next we will see what is another type of the shunt type of the generator, that is series generator. So in the case of series generator, we can take it as, so if the field winding is connected in series with the armature like this, if the field winding is connected in series with the armature, that type of DC generator we can call it as DC series generator. So this is the field winding, this is the field winding, and if you observe in this case here, so the armature current is like this, and it is flowing the same field current, and thus it is also flowing the same load current. Here it is the load we can say, and we have the terminal voltage is V here, and EMF generated we can take it as EG. EMF generated is EG. So if you write, if you apply the KCL for this, if you apply the KVL for this series generator, and one more thing you have to remember about the series generator, it is having, so let us understand what is the meaning of series generator. First we will write, if field winding is connected in series with the, if the field winding is connected in series with the armature, that type of generator we can call it as series generator. Let us consider, so because of if the field winding, if you observe the field winding nature of this series generator, it is having thick wire, okay, thick wire of less turns. It is having a thick wire of less turns we are considering. So why? Because if it is, if you observe here, so thick wire means area will be high. So thick wire resistance you are already proportional to area of cross section. So thick wire means area will be high, so that it will be resistance will be less, so that it can withstand. So if the resistance is less means, so inversely proportional to resistance, the current will be withstand high. So it can withstand high current, that's why we are taking thick wire of a less number of turns, okay. So that is why it can withstand, because it has to carry the load current also, that's why we are having the thick wire of less turns. Next, if you observe the equations of this series generator, in this equation if you observe the load current, the series field current, as well as, that is the series field current, here I have represented as IF. Let us represent with IF only, okay. So here what is the series field current is IF, and is equals to armature current. All these three currents are, let us take it as I, all are equal because they all are connected in series. Let us write the EMF generated. EMF generated we can write as V plus IARA plus ISERSE. I cannot neglect the field winding because the resistance will be, it is a less resistance means the current will be high, the drop will be also high, so the brush drop will be there. So here you have EG is equals to, we can write as V plus IA, I am taking out common because IA is equals to IF or ISE, so that is RSE plus brush drop. So if you write, if you multiply IA on both sides, EG into IA, V into IA plus IA square into RA plus RSE, next plus IA into brush drop. This is the equation. So the equations you have to remember, very important, these equations, okay. Let us move on to the next type of generators. So if you observe, next type of generators is compound generators. What are the meaning of this compound generators? In the name itself only you can understand, it is a compound generator means having a series field winding also as well as the shunt field winding also, they both are connected in case of the compound generator. So based on the generators excitation, it is a type will be a cumulative type DC generators. Next thing is differential type of DC generators. In case of cumulative generator, the phi SH, that is shunt field flux and series field flux, they both are adding. In case of differential, the shunt field flux is less than series field flux, that is a differentiation you are going to get whenever the assumption is that phi SH is greater than phi SE condition here. So based on level of compounding, based on level of compounding, also we have different types of compound generators. One is over compounded, okay, over compound. Next is flat compound. Another is under compound. These are the different types based on level of compounding. So if you observe here, so that means here NSE into phi NSE ISE is greater than NSH ISH. So that's it. So in this case, so if it is, they both are equal, NSE ISE is equals to NSH into ISH. Next is, if NSE ISE is less than NSH ISH. So these are the cases. What is this NSE ISE? Is MMF in series field winding and MMF in the shunt field winding. So if these are the cases, we will call it as the based on compound levels, we have the different types of DC compound generators. And based on connection also we have one more classification, that is based on connection. So based on connection we have two types. one is long shunt, another is the short shunt compound generators. So these are there, which is very important for the external exams. Next, if you consider what is the meaning of, we will see long shunt generator, long shunt compound generator. Okay. So long shunt generator means if the field winding is connected, across both armature, both across here field winding, first field winding, then you have the armature. So if you are connected like this type of generator, we can call it as the long shunt generator. That means if the field winding, so this is the field winding, so that is RF is connected, shunt field winding is connected across the series field winding as well as the armature, we can call it as the, what we can call, this is the long shunt generator. In this case we can write it as, so if you observe here the armature current and this is the series field current, up to this point the current is divided as, one is ISH or IF, that is IL. Okay. So if you write the equations, the terminal voltage is V here. So this is the load here, load is common. So if you write the equations for this long shunt generator, so armature current IA we can write it as IL plus ISH, or that is also equals to ISE, series field current. So EG we can write it as, that is equals to V plus IA into RA plus RSE plus brush drop. These are the two equations only you have to remember for this long shunt generator. What is the meaning of short shunt generator? So in the case of the short shunt generator, so if you consider the short shunt generator, if the field winding is connected, across only armature, if the field winding, let us see, if the field winding is connected across, that is shunt field winding is connected across only armature, this type of generators we can call it as the short shunt generator. So EG, and this is the RSE field winding, that is IS it is flowing, and this is the armature current, and this is the load current IL, and this is the field current ISH, and this is the field resistance RSH, and this is the load side, and we have the terminal voltage is V here. So if you observe this equation, if you observe this type of the short shunt generator, so here we can write as, that is IL is equals to, I can write as ISE first, then we have IA is equals to IL plus ISH. So if you want to take the ISH value, so let us subtract, we have to subtract this EG, so we will get it as EG minus IARA minus brush drop divided by RSH. What is this EG minus IARA brush drop will be V plus ISE RSE we can write divided by RSH, because only we have the EMF generated only, that is across, present across, this is only. So but we want to take ISH means, so ISH before going to get EG value we can write it as, the equation will be here, will be you have the drop of armature resistance and the brush drop we are subtracted, and ISH by RSH, and V plus ISE RSE also we can write. So we can write as, finally EMF generated will be, that is equals to V plus IL RSE plus IARA plus brush drop only. Okay. So these are the different types of DC generators we have. So in the next video we will see the introduction of the DC motor. So if you are seeing the first time this channel, please like, share and subscribe the channel. Thank you very much.